In this lesson, we're going to introduce a new arithmetic. It's called Modular Arithmetic. Fairly useful. We start with a fairly common problem. Today is Sunday. What day of the week is it after 100 days? So what day of the week really means, is it a Monday or Tuesday or Wednesday or Friday, Thursday, or Saturday or Sunday? After 100 days. So to approach this kind of question, a powerful weapon is always try to see a pattern. So let's count. Start with today is Sunday. That's today. So in one day it will be Monday. In 2 days will be Tuesday. 3 days, Wednesday. 4 days, Thursday. And then Friday, that's 5 days. And Saturday. And then in 7 days, it comes back to Sunday. Right? And then Monday, that pattern repeats. Tuesday. And again, in 14 days, it comes back again to Sunday. So here you see the problem becomes find out how many multiples 7 there is. Because after a multiple of 7, that it becomes a Sunday. And if we know that, say, for example, after 35 days, it's a Sunday, and 36 days, it's a Monday. So the whole problem reduces to just find out the remainder of 100 divided by 7 to see what that remainder is. And in here, the 100 divided by 7 equals 14 with a remainder 2. So now after 14 multiple of 7, which is 90 days, it's going to be Sunday again, correct? And then the 99 days will be Monday. And then in 100 days is a Tuesday. So for this question, the answer is a Tuesday. And we see that for this problem, the most critical element here is we only need to find out the remainder of that number when divided by 7. The quotient in here, 14, does not really matter. So there are actually quite many problems that involves only the remainder of a number divided by another number. In this lesson, we're going to introduce a notation. First, a notation, and then the arithmetic involved with that notation, which can simplify the computation involved. And that is the modular arithmetic. So first, let's see. As far as remainder concerned, 8, 1, 15, 22, 99, all those numbers are the same when I divide by 7, right? If as far as remainder concerned, they all have remainder 1. So we want to using a notation to represent that kind of equivalence. Okay, remainders are all the same. And we're going to write as 8 equals 1. Kind of equals. It's not exactly equals. And if you look at this equals, it's actually 3 lines. Okay? compared to a regular equals to 2 lines. This is 3 lines. And actually it reads as congruent. So this line reads 8 is congruent to 1. And here is modular 7 really means it's kind of divided by 7 and the remainder divided by 7. So this whole thing, 8 is congruent to 1. Modular 7 really means it's exactly the same meaning as 8 divided by 7. And I'm going to using remainder is the same as 1 divided by 7 remainder. Okay, I'm kind of using a very rough way of writing it. The English meaning of this is 8 divided by 7 remainder is the same as 1 divided by 7 remainder. So we introduced this congruence operator or congruence symbol, which write as the 3 lines, as 8 is congruent to 1 modular 7. The meaning of it is really 8 divided by 7. The remainder is the same as 1 divided by 7 remainder. One thing I want to point out is you never write this congruence operator by itself. This is always have to coupled with a modular symbol afterwards, because this is really means a remainder, and the remainder only makes sense when you refer to divide by something. So in here you write modular 7 or modular 2 or modular something. So basically with this a modular or the congruence symbol, now you can write 100 is congruent to 93, is congruent to 86, and congruent to 2 mod 7. Okay, so now every number is going to congruent with something that between 0, 1, 2, 3, and 6, because these are the only remainders when you divide by 7, right? Every number going to be congruent to one of that number between 0 and 6. How about negative numbers? A minus 5 is going to be congruent to what? If you think about all the possible remainders when you divide by 7, minus 5 is going to be congruent to 2 mod 7. And the reason being, minus 5 equals minus 7 plus 2. So when you divide by 7, this is a multiple of 7, and the remainder is 2. So you also have this negative numbers. Now basically, effectively, now you are going to divide all those numbers according to its remainders when divided by 7. And then there are only 7 possible outcomes from 0, 1, 2, all the way to 6. So basically, all the numbers are going to be belong in one of the groups. And the beautiful thing of introducing this congruence is the arithmetic involved when you're working on those just remainders mimics with the usual arithmetic. By that I mean is additions, subtractions, multiplications with numbers that of the remainders, or actually we're using the equivalent symbol. It's going to be very similar to what you have seen as usual additions, subtractions, and multiplications. And actually, we have seen that in a very, very simple example. Remember that we group numbers into even and odd. And even numbers are the numbers that when you divide by 2, remainder 0. Odd numbers, when you divide by 2, remainder is 1. And remember that we have this simple rules. Even plus even is even, right? Even plus odd, I'm going to use a simple thing. Even plus odd is the same as odd plus even. It's actually odd. And odd plus odd, okay, better to put the dd there because otherwise it looks like a 0. Odd plus odd is even. How about multiplication? And subtraction is the same as addition in the even and odd, so I'm going to skip that. And how about multiplication? Even times even is even, as the same as even times odd, and odd times even. The only case that when it's two numbers multiplied to be an odd number is odd times odd. If you're using the congruence operator to represent this, it's actually very simple. For even numbers, they are all congruent to 0, mod 2. For all the odd numbers, they are all congruent to 1, mod 2. So if you really write all those things, it's actually 0 plus 0 is 0 mod 2. Okay? 0 means even. Even plus even equals even. 0 plus 1, the usual operator 0 plus 1 equals 1, right? And here I'm going to write it's still 1 modular 2. How about 1 plus 0? The same thing equals 1. How about 1 plus 1? Now 1 plus 1 in the normal operator equals 2. So equals 2. But 2 divided by 2, the remainder is 0. So it's equals 1 plus 1 equals 0. And which is odd plus odd equals even, is equivalent to even. How about multiplication? 0 times 0 is a 0. 0 times 1 in usual operators is equals 0. In here, it's also equals 0. Even times odd equals even. And the only case when it's generates an odd is odd times odd. Usual operator 1 times 1 equals 1. So here it still equals 1. It is congruent to 1 modular 2. So here, this can be actually generalized into any modular n. I'm going to just using some examples to show it. I'm going to introduce start. I'm going to use some examples to show the operations in the modular. It's going to be very similar to the usual operations. So here, I'm going to using two numbers. We know that 100 is equivalent to 2 modular 7. And let's use another number. 25 is equivalent to 4 modular 7. Remember that really means that 25 divided by 7 is remainder 4. Now, let's see the first thing, addition. If we talk about 100 plus 25, if we take this number divided by 7, this is actually going to be the same, equivalent to 2 plus 4 modular 7, which is equivalent to 6 modular 7. So this simplifies the addition. Like our usual way of doing this, like to find out the remainder of 100 plus 25 divided by 7, is you can add them up and then divide by 7 and find out 6. In here, I'm actually dividing to find the remainder first of the 100 and the remainder of 25 first, and then by adding them up, it simplifies. In here is a little bit. How about subtraction? 100 minus 25 is going to be equivalent to, or congruent to, 2 minus 4. Congruent to minus 2, but minus 2 is congruent to 5. Mod 7. So for congruence, we always, in the end, we want to map back to some number between 0, 1, 2, all the way to 6 when it's divided by 7, because these are the only possible remainder when I divide by 7. And every number is going to map one of such remainders. Okay, the biggest benefit coming from multiplications. So let's see, 100 times 25. If we want to ask what's the remainder of this number divided by 7, this is the same as 2 times 4 is the same as 8. Of course, that's 1 modular 7. Now in here, you see a huge benefit, right? A usual way of calculating the remainder of 100 times 25 divided by 7 is you're going to multiply this thing out, and then you divide by 7, which takes quite a bit of long division. But in here, you can do the division first. Find out remainder of 100 divided by 7, and then remainder of 25 divided by 7. And then you're doing this very simple operation. Okay, so this congruence, this modular arithmetic, makes sure this is correct. The benefit of this modular arithmetic is evident from the next example. This example goes like this. Problem: what is the remainder of 8 to the power 100 divided by 7? Now, it is clear that it is impractical to calculate it 8 to the power 100 and then divide by 7. If you're using the modular arithmetic, this 8 to the power 100 is congruent to 8 times 8, of course, times 8, 100 times, right? But each 8 divided by 7 is remainder 1. So which is congruent to 1 times 1 times 1, 100 times. And this is congruent to 1, modular 7. So this problem can be handled very, very easily by using this modular arithmetic. Okay, so in this class, we introduced this notion of modular arithmetic. It is very basic properties, and we see that the biggest benefit is from multiplication. That's the end of this class.